At KRATON Performance Polymers, our highly engineered synthetic elastomers are used to enhance the performance of products that touch the lives of people around the world. With manufacturing facilities on 4 continents, we offer some 800 different products to more than 700 customers in 60 countries around the globe. As the original inventor of SPC chemistry in the 1960s, KRATON has a history of innovation dating back over 50 years. That commitment to innovation is the driving force behind our portfolio of higher performing polymers that address a challenging range of paving applications for roads and highways.
We think of our business as not just a producer of styrene-block copolymers, but we think of our business as being the enabling ingredient for our customers to meet their demanding market needs. Our paving and roofing business is primarily focused on developing technologies that extend the useful life of roads and roofs in so many different applications in so many different temperature and climate environments around the world.
KRATON Performance Polymers is the only producer of styrenic block copolymers that has a global network of manufacturing plants. Our state-of-the-art facilities are located in the United States, Germany, France, Brazil, and Japan.
Around the world, road owners face increasing traffic loads and rising maintenance costs, which lead to the growing demand for higher performing roads and creative solutions ever tightening budgets. That's why we're excited about our new highly modified technology platform, or HiMA, that leverages KRATON's low viscosity polymers at a 7.5% modification level.
To develop the next generation of products and provide technical service to our customers worldwide, we have invested in innovation centers in Houston, the Netherlands, China, and Japan.
When we started to think about this project, and that was in 2005-2006, our company had also developed a new polymer. And that polymer was specially designed to give lower viscosities, to give better compatibility. With the highly modified system, we have been able to improve on the fatigue resistance to such an extent that we could reduce the overall thickness. We really needed to prove what we had, and therefore we went to the United States and we put into trials in many states. But the most important one, I would say, is the trial that we set up in NCAT together with the Auburn University.
The basic guide for designing asphalt to go into pavement is the temperature range that the asphalt needs to be able to span. It needs to be stiff enough at high temperature to resist rutting and soft enough at low temperature to resist cracking. For pavement structures further down where there's not so much temperature swing, there's no need for modification. Well, that theory works as long as you're designing a conventional thickness, but we began to wonder a number of years ago, if we use the benefits that we can get from modification to really boost the performance of the material, can we actually make the pavement thinner and still get it to perform well? The tests we have done to date on mixtures with them show that we get dramatically improved resistance to both rutting and to cracking.
To validate our technology, this innovative product went through a series of tests at the National Center for Asphalt Technology at Auburn University. NCAT's Research Center and Test Track make it one of the world's leading institutions for asphalt pavement research.
NCAT's mission is to improve the quality of asphalt pavements through applied research, education, and technical support to the contracting community in the United States. After we have built test sections on our track, then we start our fleet operations. We compress 10 million easels, or equivalent single axle loadings, which is approximately 6 million heavy axle passes, into these 25-month trucking cycles. The high polymer binder was included as a treatment with all 3 layers that are included in the buildup. So that constitutes about an 18% reduction in thickness in the experiment on the track compared to the standard 7-inch thickness in the experiment. And if that technology is applied out in the open infrastructure, that could either result in thinner layers or possibly the elimination of layers in the pavement. Our experience with the thinner high polymer section has been very positive so far, and performance compared well to the other thicker conventional pavements. Subsequently, a nearby test section sponsored by state DOT had completely failed, so we had a big maintenance need that came up. So we proposed to them the option of using high polymer mix this time not for the full depth pavement, but as a rehabilitation mill and inlay. It's very helpful to us to determine what the structural contribution of all the different materials are, and that's helpful for both new construction and rehabilitation. But much of the nation's infrastructure is shifting into a preservation mode, so it's important that we collect data here at the track so we can inform state DOTs on how to make the best use of their preservation investments.
This advanced technology is not only an effective solution for structural pavement, but it also shows great promise for non-structural fixes such as cracking or rutting.
Utilizing the information that we've gained from working with the University of Delft's technology group and their modeling group, as well as the data that we've generated at the test track at Auburn University, we feel that the HiMA technology platform can easily be translated to pavement preservation products such as thin lifts and emulsion treatments like chip seals and microsurfacing.
As part of the AASHTO program, Dr. Walla Mogower, director of the Highway Sustainability Research Center at the University of Massachusetts, was requested to evaluate samples.
In collaboration with the members of the Northeast Pavement Preservation Partnership states to develop a spec for high-performance thin lift, but these are basically performance specifications. So we're testing these mixes and how good they are in retarding reflective cracking, how good they are in resisting thermal cracking, and also we look at rutting. For these type of thin lifts, we included in the spec as many tests as possible. The data it will be posted on AASHTO TSP2, whether it meets or it doesn't meet, all the data will be posted.
In New Hampshire, the extreme swings from frigid winters to warm summers pose unique challenges to pavement. As Dennis Boisvert, Chief of Materials Technology at New Hampshire's Department of Transportation explains, KRATON's HiMA technology could be the answer.
The things we're trying to resolve are basically cracking, reflective cracking, short-term flaws in the pavement to keep the water out of the bases. Select materials need to stay dry or we get differential heaving, which brings on more cracks. So we're always looking for the next best thing there. The battle being balancing additional costs against additional benefit. The benefits of the polymer binder are attractive because it broadens the PG grade or range of the temperatures, which should give it the material much more elastic performance, which will help to bridge those cracks and keep the rainwater and snow out of the select materials.
Kevin Prince, pavement management engineer for the New Hampshire Department of Transportation, talks about the deciding factors behind implementing KRATON's HiMA technology.
We have a pavement management committee, and it consists of people from design, construction, materials and research, and pavement management. We look at the roads, we discuss it, we decide what we're going to do to that road for pavement management. We have more roadways than we have budget, so that committee sits down, looks at these roadways and decides, okay, which would be the better candidate, and then decides, should we go with, a chip seal or a microsurfacing or thin lift overlay or any other suggestions.
Next door in Vermont, KRATON's HiMA technology is also being put to the test. Michael Fowler, pavement management engineer for the Vermont Agency of Transportation, discusses the road issues they are facing.
Since about 2006, we've started pursuing a preventive maintenance program, and that's really grown significantly since then. I'd say the meat of our preventive maintenance program is the thin overlay. We worked with Professor McGower, the materials engineer, worked directly with him to ensure that our specification was going to suit our needs, as well as maintain the integrity of the evaluation. The existing pavement was a 1997 treatment, so it was 14 years old, and was, as with any hot mix, it was getting a little tired, but it was performing still pretty well. We hit it, I think our timing was really good. It was business as usual, as if it was any other super paved mix that they'd been working with in the past. I don't even know if they even knew it was different. If they hadn't been told, they would have never known that this was a material that they had worked with previously.
KRATON clients are impressed with the performance characteristics of HiMA, as proven in their own lab studies and at the NCAT test track. In Brazil, Compassa, a major contractor in that country, is using HiMA in the rehabilitation of roadway PR-092 in the state of Parana. By leveraging HiMA technology, Compassa is reducing the pavement wearing course thickness by over 4 inches, a 40% reduction from the original specifications. In countries around the world, across a range of climates and geographies, HiMA technology is paving the way to superior road performance and longer road life.
This technology allows road designers the capability to decrease pavement thickness in the base, binder, and wearing courses between 30 and 50%. They can achieve superior rutting, crack resistance, and durability. Incorporate both hard and soft bitumens with full polymer compatibility. The result is going to be lower upfront cost savings, reduced ongoing maintenance costs, and ultimately more miles paved.
For more information on our highly modified asphalt technology, visit pavewithkraton.com.